All right, good afternoon, everyone. We'll go ahead and get started today. Thank you for the patience with the technical issues. So it's my privilege to be able to introduce our seminar speaker today, Professor Carmel Majidi, who's the Clarence Adamson Professor of Mechanical Engineering at Carnegie Mellon University. At CMU, Professor Majidi also has courtesy appointments in the Robotics Institute and the departments of biomedical engineering, electrical and computer engineering, civil and environmental engineering, and biomedical and material science. You have them all.
Yeah. Well, I studied in all those programs. Yeah, in all those programs too. So
prior to joining CMU, Professor Majidi earned his PhD from UC Berkeley, where he then went on to do postdocs both at Princeton and Harvard. Where at Harvard he began his work in this whole area we're going to hear about today of soft materials engineering for devices and robotics with Professor Robert Wood. In addition, for all the recognition that he's done, Professor Majidi received a number of awards, most importantly, Young and Early Career Investigator Awards from DARPA, NASA, the Air Force Office of Scientific Research, and the Office of Naval Research, to name a few. With that, I want to make sure he gets as much time as possible, so please join me in welcoming Carmel.
thank you, Brian. It was a real pleasure to be here. I've so many of you kind of seen virtually, over the years, and great to finally meet in person. And so I'll just kind of jump right into it. Apologies for a little bit of the technical delays, and also apologies to folks on Zoom who there might be this delay also, I think, in some of the slides updating. But in any case, as Ryan said, I'll be presenting our work on kind of what I call soft matter engineering. It's kind of a term I kind of quasi made up. It's really just an adaptation from soft matter physics and kind of studies of condensed soft matter and how they could be used in robotics and wearables and other domains of engineering. First off, I do want to acknowledge my research group has done all the work. I'm just merely kind of an ambassador here, just to share all the exciting stuff that they've done. I have these appointments in all these different departments, and my students come from all these different departments. And so it's a very interdisciplinary group, a lot of diversity in terms of people's research background and interests, and then kind of where they're taking some of this work. So just real quick, I mean, when I think about soft materials engineering, really the idea here is to achieve the pretty much the same functionality in computing and robotics that we typically achieve with hard materials, and replicate a lot of those functionalities with soft materials in terms of the actuators and sensors and electronics, but still preserve a lot of the kind of the elasticity and the rheology and the mechanical properties of soft matter, so we can better mimic the properties of natural biological tissue, and also create wearables and human machine interfaces that can be comfortable and safe for direct physical contact with the body. So this is something that we generally think of as an important element of soft robotics. Ryan mentioned Rob Wood, who's kind of really done a lot of really exciting work in this space, but there's plenty of others. Ryan himself has done a lot of really exciting research, and there's just been decades of work. Actually, you can go back to the 1950s and 1940s, and then folks have been doing soft robotics work with kind of soft materials, elastomers, using pneumatics, hydraulics. A lot of these concepts and material architectures actually in some ways predate a lot of the current practices and just the field of robotics more generally. So a lot of rich history here, a lot of work to build on over the years. And it's not just soft robotics. There's been also decades of research on all sorts of robust, deformable, kind of skin-like electronics and sensors. Of course, Northwestern is the hotbed for a lot of this work. Really the gold standard in stretchable electronics is really kind of established here. With folks like John Rogers and Hong and then and others, with these kind of more deterministic architectures using kind of wavy and serpentine ultra thin film electronics, but also a lot of really exciting work with nanomaterials and then soft composites. I'll talk quite a bit about our work with using liquid metal, and then also with hydrogels. I'll kind of touch on some of the efforts, not just with ionic hydrogels, but actually more recently electrically conductive hydrogels that kind of expand the range of options for stretchy electronics and sensors. And then tying into some of the strengths here at Northwestern. Again, not just on the stretchable electronic side, but obviously on the haptics side as well. The work done by at Colgate and others and really kind of pioneering kind of, novel material architectures, material systems, and using those for haptics and human machine interaction. So this represents another really kind of exciting area where, there is that continued potential for soft materials engineering. And then lastly, when we talk about stretchable electronics and these kind of artificial skins, that ties into, wearables, wearable computing. And then the big question, of course, is how do you power these systems? And so wearable energy harvesting is kind of another area that's kind of getting a lot of attention right now. So I'll kind of touch on this a little bit in the talk as well. Okay, so I will just, fair warning, this presentation is going to be a bit of a data dump, just because, I don't think I need to educate you on any one of these topics. I mean, there's already a lot of amazing work, here, and then, you guys are in a lot of these domains more of an expert than I am. So really, my job is just to kind of just give you kind of just a kind of array or, general sense of all the type of work that we do in my group and how we're contributing. And hopefully some of this, triggers some excitement for collaboration, right? I mean, that's really kind of what I'm looking for here in my visit. So I definitely want to see if there's ways that we can kind of work together on a lot of these topics. One of the common practical challenges that we find at when we start applying soft matter engineering or applying soft materials to problems in robotics and wearables is this issue of materials interfacing, right? Inevitably, you're going to have rigid microelectronic chips or components, motors or whatever, that interface with your soft materials. And so having robust interconnects, having versatile manufacturing methods to integrate these materials, pattern them at these various length scales, that kind of it has been a challenge for us and will continue to remain a challenge. It's not necessarily the kind of the sexiest aspect, of engineering. It's not, the aspect of it that necessarily, comes to the forefront in terms of the science, but as far as I'm concerned, that there is kind of important kind of scientific questions here as well in terms of the, how we actually interface these and integrate. But the ultimate goal is that we want material systems that either kind of locally or at least kind of globally, at the systems level, kind of have a lot of the mechanical properties that match features of soft biological tissue and organisms. The first half of this talk, I'll kind of just give you a quick overview or I'll kind of quickly go over all the different projects we've done kind of in the space of artificial skin, wearable electronics, and I'll mostly emphasize work from the past 2 years. And so I'll try to kind of keep this up to date, especially for those of you who are, just generally familiar with this field and what's been happening in the past decade. Again, there's all sorts of material architectures in stretchable electronics, wearables, and I would say, my group, we haven't really done anything pioneering in any one of these areas, right? We were always, as most, engineers, quite honestly, we're just building on, basically, building on the backs of others, really, and so, with any of these topics, I mean, we kind of either will dabble a little bit, try to make some contributions that could be useful, from a, manufacturing standpoint, making these, more easy to kind of prototype or to utilize in certain systems. But there are certain areas, especially with liquid metal, where we are, trying to stay a little bit more at the forefront and really exploring what is possible with these material systems. So some of these topics I'll kind of touch on briefly, and I'll kind of spend a little bit more time on the liquid metal stuff. And so, this is something I don't have to motivate. I mean, most all of you are, we're at Northwestern, right? So you're already familiar with these architectures of achieving high degrees of flexibility and stretchability, just by simply taking your kind of conventional electronic materials that are used in printed circuit boards and just introducing some kind of deterministic patterning to make them stretchy. So whether it's in-plane springs, whether it's these thin films that have kind of these wavy buckle structures, there's all sorts of lithographic methods to create these architectures. In my lab, we just found that just simple UV laser micromachining is good enough to create a lot of these same systems. Granted, at somewhat of a larger length scale, but still small enough that we can directly interface with pretty much any kind of surface microelectronic chips or sensing components that we need for different types of wearable applications. So this is just kind of one case of a finger-mounted pulse oximetry chip this video. Sorry, it's a little bit dark here. But this is actually work quite a few years old now with Lining Yao in our HCI Institute, who developed a kind of a software interface to allow non-experts to go in and design some of these wireless sticker-like technologies that use these laser patterned serpentine interconnects to do multimodal sensing on the body. And so I'll skip ahead here in this video just in the interest of time. What we can see is that we can actually produce these using rapid prototyping techniques and create these customized stickers in under an hour. And they're fully wireless. We can kind of incorporate, Bluetooth just like you would with any kind of standard IoT device or wearable. And this kind of particular use case is a pair of IMUs, so you can do kind of joint angle sensing. Maybe a little bit easier to see on that monitor than the projector, but the next clip just shows you just how robust and stretchy these serpentine interconnects are. So this is obviously well known, prior to us working on this. But what we kind of show is just that, once you have kind of a rapid prototyping method, you can achieve all sorts of different sensing modalities just using these surface mounted commercial chips. So acoustic sensing, IMUs, pulse oximetry, temperature, pretty much the works there. So, very, promising approach. Still, I say represents kind of the gold standard and probably the most mature approach to creating stretch electronics. But one of the challenges, of course, is that, when we say deterministic, like you actually have to engineer that patterning into these materials to get that stretchability, right? And so what these materials are lacking is that intrinsic kind of compliance and deformability that you truly need if you want to have something that really matches the mechanical properties of soft biological tissue at all the different length scales, right? So I'm not going to get into all the downsides and challenges, at least for us practically working with these kind of laser pattern electronics, but needless to say, there are kind of cases where we want to shift to these other material systems. So with these kind of particle filled composites, again, this is another really rich area, fairly mature at this point, and over 100 years old. I mean, back to, actually, the turn of the last century. I mean, folks were taking carbon black, carbon powder, filling it into rubber, achieving percolating networks that had electrical conductivity to get all sorts of kind of soft rubbery conductors. And so if you use carbon black, the conductivity is quite not enough for digital circuitry, but it's enough if you want to have like capacitive transducers or resistive transducers to do some basic, say, touch sensing. This is kind of work we did with Jorgen Semmel and a few others years back on using these as kind of little tactile interfaces. But then more recently, switching from carbon black to, say, silver flakes, you can actually achieve the high conductivity you need for digital electronics. So this is something that, again, is still fairly mature technology. It's not something that we by any means have introduced, but what we have kind of contributed to are just ways that you can manufacture these circuits in a much more rapid way. So you can kind of create these kind of customized sticker-like wireless devices that you could do for multimodal sensing. And I'm not going to get too much into these architectures. We had a spin-off company a few years back that looked at starting to commercialize these for wearable health monitoring. What I do want to spend a little bit more time on is kind of a more relatively more recent discovery. And this is something that I should emphasize after we kind of came out with this publication. Other groups I would say maybe independently kind of discovered a similar type of architecture, right? So there's kind of various versions of this now in the literature that you can find plenty of people to kind of collaborate with if this is something you want to kind of work on or learn more about. But the basic concept here is we're taking that same kind of particle-filled architecture that's used for those stretchable electronics, but now instead of just looking at electrically conductive particles, now we're using these ferromagnetic particles that we can actually permanently magnetize. And the value of having these magnetic microparticles inside rubber is now you can create these transducers that can translate or map changes in kind of shape or mechanical deformation now into changes in internal magnetic field. And so one of the nice things about this approach to the sensing versus kind of what I showed you before is that with this approach, you can actually get continuous sensing over this kind of relatively large area and achieve that continuous sensing all with just a single sensing chip. So you just need a single 3-axis magnetometer. And then with that, you can kind of resolve both the intensity of contact, say pressure, and also the location of pressure on this continuous area, right? All the architectures I showed you before, basically you needed a one single dedicated chip for every kind of location spatially where you wanted to detect contact. And so that leads to this kind of, issue with scaling up and having all the wires, wiring needed to kind of connect to every single one of those discrete nodes where you want sensing to happen. Here, we just have our single magnetometer. There's this liquid metal wiring, I'll get into this later, that we use so that the circuitry used to support that 3-axis magnetometer can kind of stretch into form with the surrounding magnetic rubber. So, yeah.
A question about that.
Sure.
So you're still just getting 3 numbers out.
Yes.
Of the magnetometer. And it's somehow related to all the different kinds of deformations that you can get.
Correct.
So how do you solve that problem?
So it's the direction of that magnetic field and how that changes, but also basically the magnitude of the change in the magnetic field. That's a very crude way of kind of establishing the location and intensity of contact. And you can train a machine learning classifier to be able to achieve that continuous sensing, but it's going to be pretty crude and the accuracy is going to be somewhat poor. And so usually if you have maybe not just 1, but maybe 2 magnetometers or 3, but still distributed over a large area, then you can get very rich, a pretty good resolution, kind of, millimeter scale, maybe even sub-millimeter scale over that continuous area.
So at the basic level, you're turning those 3 magnetometer readings into 2 location coordinates. And then intensity.
Correct. Yes, that's exactly it. Yep. Yeah, that's a great way to think about it. Yeah. So yeah, but needless to say, I mean, this is a highly stochastic mapping, right? So I mean, we can't just use some type of FEA or something to kind of establish what that relationship is between, say, surface pressure and change in magnetic field. And so here's, we would just have to use, a classifier or kind of a regression scheme to do that. So this is something that Tess Hellebreakers, one of my former PhDs, she developed this material technology, something she kind of almost discovered as an accident, and then just started working on kind of developing that with some other folks at CMU who kind of specialize in AI for sensing applications. So, here's this kind of giving you a sense of this, little fun little demo using this. Now here, we're not really using continuous sensing. We basically just want to sense of these 4 locations, but you can have any arbitrary number of buttons, right? You just kind of put the buttons wherever you want it, and you have that 1 magnetometer. So long as you kind of train your classifier, then you can use it to have that touch interface, and it's fairly robust. So this is still ongoing. Tess has continued to work on this project. She's actually now at Meta AI, and I have another PhD student right now who's a Meta fellow who's continuing to work on this technology. This video here just shows you some really basic use cases of it. What's actually interesting is with this magnetic, because it's kind of based on magnetic field, we can also use these sensors for proximity detection as well. So if you have the magnetometer, say on the robot finger, and if you have this magnetic skin on the object that you're trying to interact with, say, then you can actually also not just detect pressure during contact, but also detect the proximity as well. Here's just an example of using the skin just to kind of modulate the pressure to kind of get different droplet sizes out of that pipette. And then the next video here, and again, sorry I'm going through this so quickly. I just want to kind of touch on a bunch of these topics. So definitely stop me if you have questions. Yes.
So capacitance sensing also works non-contact. I'm curious what your take is on the advantages of magnetic field versus passive, non-contact sensing?
So yes, that's a great point. With capacitive sensing, at least the architectures that I know of that could do capacitive sensing over a continuous area with just like couple of electrodes. Those can determine location. I'm not aware of any that can decouple the location and the intensity of the pressure, but I could be wrong about that. So, because there's also kind of resistive sensing, these piezoresistive type masks, but those usually need like column or row addressing to do that. So those require a lot more in terms of kind of wiring to do. But certainly capacitive is good. I think if you're just trying to determine just the space, the location of the contact, you can just do that with electrodes at the four corners of your surface, right? And then usually that's good enough. Let's see, I don't know if this, here it goes. So this video seems to be a bit choppy. So let me see if I can just play it in the edit screen here. I'm going to skip this video just because it seems it's kind of holding up. We can get back to it later if you guys have questions about the reskin. But anyways, I mean, I think that kind of represents just kind of another way in which we can use these kind of particle fill composites to achieve these capabilities that could be useful in robotics. So I'm going to spend a few minutes talking about our work with a liquid metal, just because I feel it does have this kind of best of both worlds type of property, that it's a metal, so it has high electrical conductivity. It has also high thermal conductivity for cases where that's important, but it's a liquid, right? So we can incorporate it into rubber, either in the form of microfluidic channels or little micro scale or nanoscale droplets, and it doesn't really kind of interfere with the kind of the natural mechanics of that surrounding rubbery matrix. And there's all sorts of applications. Folks throughout the world have been looking at this increasingly. Companies now have been kind of interested in uses of liquid metal for a range of applications. And so this is a really kind of rich area of research. And at this point, I mean, we have kind of manufacturing methods and synthesis techniques where we can kind of pattern and incorporate liquid metal into gels and elastomers or other kind of soft matrix materials at all sorts of different length scales. And so I'll just quickly touch on just some of the work that we've done with liquid metal based microfluidics and how we can use that for creating highly robust and flexible and stretchable electronics. This is a visual circuit made out of the liquid metal, just directly interfaced with all sorts of microelectronic components for sensing and for signal processing, communication. Again, some of these videos might be easier to see it on the TV display there. But here's this kind of one of our kind of early attempts at using it as a sensing skin for a soft robot gripper. So this is a simple two-finger gripper where we have a liquid metal functioning as a kind of a pressure sensing transducer, but then also using it for electrical wiring, for a time of flight sensor, for doing scans, also for connecting up an IMU for tracking kind of motion orientation of the robot, of the gripper, I should say. And just in this next clip here, you'll see that by kind of incorporating all this sensing, using a skin that is itself kind of soft and rubbery and stretchable, it doesn't, impair the ability of the robot to operate, and then it endows it with the sensing capability so it can kind of be robust to any kind of disturbances. So like for this case, if we move the chest piece, that's something that was kind of detected by the time of flight sensor. And then say if we kind of interfere with the gripping of that chest piece, as you'll see here in a sec, that's detected by the liquid metal pressure sensors. So again, kind of, using that kind of onboard sensing, relying on more than just computer vision, or a camera to give the robot, some degree of kind of autonomy so it can complete a task. All right, so that's kind of, almost state of the art, kind of where we are with microfluidics. Pretty much, really anything is possible if you're talking about just, these simple kind of strain sensing or pressure sensing applications, or if you're looking at using these for stretch circuitry. Anything kind of more complex really relies on the multifunctionality of these composites, where instead of fluidic channels of liquid metal, we have these kind of microscale or nanoscale droplets of rubber suspended within the matrix. And so this is kind of, one of the things that the architectures that we discovered a few years back, where we found a kind of a really kind of rich and kind of unique combination of material properties. So combining the whatever the kind of the innate native mechanical properties are of that surrounding gel or polymer, but then combining that with kind of metal-like electrical conductivity, thermal conductivity, and also endowing these polymers with enhanced fracture toughness, and in some cases, the ability to kind of self-heal and repair themselves. So I'll kind of touch on that a little bit later if there's time. All right, so in some cases, we can load up these polymers with 50% by volume liquid metal droplets. That's what you see here. We can actually go up to like 60, 70, even in some cases 80%. And so in a lot of these cases, it's actually mostly metal. So these materials are actually quite dense, quite heavy, but because the inclusions are liquid, the composite's still quite soft and rubbery. And so we can have these materials that have these really enhanced thermal conductivity. I won't have time here to kind of get into the underlying kind of physics of these systems and how the thermal and electrical properties can be predicted using principles like effective medium theory and then other principles in mechanics or physical mechanics. But the thermal conductivity itself is important. If we want to use some of these soft material systems for applications like wearable thermoelectric, so if we want to do active heating or cooling on the body, on skin, if we want to do thermoelectric energy conversion, so if we want to actually convert body heat into electricity, well, it turns out that these liquid metal filled composites do a much better job in terms of allowing heat to kind of flow in and out of these thermoelectrics so that they can kind of operate. And so, with these composites, I won't get into this, but we can also 3D print them using just basic kind of extrusion-based techniques, and we can even create these kind of 3D-like architectures to create little heat fins and things like that to further improve thermal performance. And so this is just kind of one example. We've had a few publications just on the thermoelectric device itself, and we kind of have this current study here where we're still kind of wrapping things up. We're just kind of finishing up our treadmill studies to show that we can fully power a Bluetooth transceiver, a microcontroller, and also a pulse oximetry chip for doing heart rate and blood oxygenation monitoring, all entirely with energy powered from body heat. And so we basically use these like thermoelectric, soft thermoelectric pads with that liquid metal filled composite. And then, this is just some preliminary results. I mean, we've had some more actually since then that just shows, some of the voltage output that we can get from this. So power outputs are actually quite good. I think we're talking, milliwatts per square centimeter, which might sound small, for a lot of kind of the more power hungry devices, but actually is kind of enough for Bluetooth low energy and some of these low power sensing devices. So that's it for thermal conductivity. We can also make versions of these composites that have very high electrical conductivity, and combined with that, also very low electromechanical coupling. So you can see here that as we stretch these materials, the resistance, the conductivity actually remains quite stable. And so it doesn't kind of spike up the way you would expect for materials that are conductive. As they elongate and then cross-sectional area decreases, you would typically expect resistance to spike up. We don't see that with these composites. We've done quite a bit of modeling just to validate what we're seeing experimentally there. I won't get into it. Here's just kind of another version of that, where to make these even more stretchable, up to 1,000% strain, we can introduce these kirigami patterns, cut splits through them, right? I mean, so there's kind of stuff that we can do there. And again, why this is significant, from a wearables standpoint, is that now we can, look at other energy harvesting modalities. And so here's an example of triboelectric energy harvesting by using these conductive liquid metal rubber composites. And so we're basically using these as these pads that come in repeated contact with the skin, say during something like activity like jogging, And that produces, just through basically produces triboelectric charge. And then, with subsequent contacts, you basically change the, you're kind of varying the capacitance, and you can actually convert that into enhanced voltage that you can then harvest. In this case, we're harvesting that energy to power this body-mounted device. So, in this example, this is kind of a very crude kind of first pass at triboelectric energy harvesting with these devices. So it takes about 15 minutes of jogging on a treadmill. But once when you've kind of primed up and kind of created that charge, then, every, 15 seconds or so, you can kind of basically recharge that device and collect data there. So just kind of another energy harvesting modality. So the last topic on this, on the liquid metal that I want to touch on before we move on is with these kind of printable versions of these conductive inks. And this is kind of, for us, kind of what we're currently using now for a lot of our sticker-like electronics for physiological monitoring. So we can do all sorts of pattern these to create all sorts of different types of bioelectronic sensors for EMG, ECG, EEG, and also directly interface with various surface mounted components. So, I do want to kind of move along here just because I did get off to a little bit of a late start, and I want to make sure I get to the soft robotics content. So the gel stuff, I'm just going to kind of skip through. Bottom line here is that, we know there's cool stuff that we can do in terms of, making soft batteries with gels. We can also make systems that are even more compatible with the body. If we want to make these soft kind of bioelectrodes when we use gels as the matrix material. I'll let this video run a little bit. This is kind of a fun example of using the gels now and actually reconfiguring their conductivity. So the nice thing of gels, as opposed to say a silicone rubber as our matrix material, is now we can actually use kind of hydration and dehydration to increase or decrease the conductivity in a kind of a reversible way. So here we're decreasing conductivity for the motors for the wiring on the left. And so you see the motors on the left side, don't move quite as much. And then here now we're going to hydrate the kind of the connection, the motor neuron, if you will, on the right, and you see that those motors now won't kind of move quite as much. So these are some of the emergent properties that come just by virtue of now shifting from your typical printed circuit boards now to these kind of soft, gel-like materials. And so you start seeing behaviors that it's some very loose way start to mimic the properties of the kind of, natural nervous tissue and their neuroplasticity and reconfigurability. And then I'll skip this. This is just another quick example here of a soft snail robot. Oh, actually, no, sorry. This is just a conductive gel that uses liquid metal, gel, and also surface flakes. And has this nice tacky self-healing property. So you tear it apart, stick it back together, the electrical conductivity is restored. The elasticity is basically material integrity is restored. So you see here, this is a real-time video showing our magic self-healing conductive gel connecting a motor with or a controller. This is all just an untethered soft robot here. We cut at it. We don't fully sever it, but we cut it out enough to, reduce the conductivity. So, the motor slows down, and then just simply by just tamping on it, right, that basically gets the material to stick back to itself. So it kind of has this self-healing property. So again, something that you just wouldn't get with, your printed, your copper-based PCB. So anyways, a fun project, and maybe useful if you ever need a soft snail robot. Okay, so I'm going to try to cram in several students' PhDs into the next 5 minutes here. Again, sorry that I'm going through this so quickly, but I just touched on kind of one aspect of soft matter engineering, right? Which is kind of the the robust electronics and the sensing and to some extent energy harvesting, right? But then there's a whole other question about how do we actually build fully untethered soft robots, that are capable of dynamic motion, that are untethered, right? actuation, of course, that's the, the big question. And so, this is something I'll just kind of briefly talk about. And then also kind of what are the considerations when it comes to actually achieving autonomy with these systems in terms of, control and how some of that could be guided by simulation. So again, apologies, I'm kind of skipping ahead here. We're using shape memory alloy. In place of using pneumatics or motors, just because these materials have very high work densities and they can be quite compact and capable of pretty robust motion. So these are all real-time videos showing untethered soft robots that are fully powered using shape memory alloy actuators. This is kind of for dry conditions. Here's just kind of a few examples of these swimming soft robots. And, if we put markers or QR tags or whatever, and we have a camera set up, we can also do, have it perform some really basic tasks like, following a little ping pong ball in a water bath. So, there's nothing too, I think, groundbreaking about these material systems. It's just really just a matter of engineering them in a way that we can leverage those SMA coils basically to get these robots to move and operate within an environment and do so fully untethered, which is again a nice advantage of using SMA versus some of the other soft robot actuation techniques. Something though that we found that if we ever want to control these robots and do something useful, we really need to have, ideally we would like to do model predictive control. That would be, I think, the ideal. But what we found is to get there, it really helps if we have, some good model and then some good way of kind of simulating these soft robotic systems. So, this is, an area that, Sam and then, Josh Wongard and, Tom Lipson, Daniela Roos, plenty of have kind of looked at. Stelly and Koros have looked at kind of creating these doing these kind of sim to real type representations, for soft robotics and creating these kind of physics engines for soft robotic systems. A lot of our work uses a practice in computer graphics known as kind of the discrete elastic rod model. So this is actually work that I adopted from a former postdoc in my lab who's continued to kind of work on this. And so this is the work that we did together on building a soft robot physics engine that actually runs faster than real time. So the time it takes to actually generate the simulation is basically faster than the wall clock time of the physics that it's actually trying to simulate. And a lot of our effort has actually been in trying to experimentally validate those physics engines with some of our soft robot test beds. And so don't have time to kind of go through all the details here. But the agreement is actually quite good, not just qualitatively, but quantitatively. And so what that means is that now we can actually use the physics engine to start designing and controlling these robots and doing things like path planning. This is kind of showing it now, applying that physics engine now with a simple kind of fluidic model. And again, doing these kind of faster than real time simulations. This is kind of, one of our more recent studies, simulating these kind of frog-inspired soft robots. And so now if we want to do, say, something like path planning or trajectory following, instead of having to collect a lot of data on the soft robot, we just do everything in simulation. We generate like this whole library of motion primitives, and we try to predict basically how the robot's going to behave, say in this fluidic environment, if it moves its limbs in certain ways. And then, so when it comes to showtime, and we ask this robot to kind of move along a certain path, now it has this huge library of simulation generated motions that it can draw from to decide, after every few steps, what it needs to do to kind of correct its trajectory and kind of get on back on track. And so that's kind of some of the stuff there. Again, though, you can see that, we're still using computer vision here to track. There's no onboard sensing. The robot has no sense of where it is in the world, right? We still need a radio to go and track its motion and send commands back to it, right? And so the idea now is if we can actually incorporate sensing into these soft robotic systems. And so that's something that some of my PhDs and former postdocs are kind of working on. Sorry, these videos for whatever reason are not playing. Let's see if I can skip ahead here. So this is just kind of that same shape memory alloy powered soft robot limb, but now we put this soft bend sensor, and this actually uses the capacitive sensing that you were talking about. So, quite robust. It allows us to detect motion both in plane and out of plane. There's this anti-wind-up feature of the controller that we're using, something that Drew Sablehouse, the former postdoc, introduced in this. But the ability to kind of follow certain trajectories and use this feedback control is quite good. So long as we use that anti-wind-up basically to prevent the pulse width modulation from sending too much current to our SMA coils to cause overheating. So that's kind of a big concern when you use these. Here's this kind of another approach based on trajectory optimization on a different kind of robot limb design. This is basically on a based on a model. So we have a desired trajectory, then we have the model generate what the commands need to be to those SMA coils to as close as possible track that trajectory, and then we go implement that on the robot limb. Again, just in the interest of the time here, I'm just going to skip ahead. And the reason I'm kind of eager to skip ahead here is because I'm really want to share before I wrap up here some of our work with liquid crystal elastomer, just because this is something that actually builds off of inspired by work that Ryan has done, kind of in using LCEs, and in this case particularly kind of 3D printed LCEs to create all sorts of interesting soft robotic systems. Our contribution is basically to take those liquid crystal elastomers, those shape memory polymers, and incorporate those liquid metal microdroplets inside to make them electrically conductive, so that we can make them basically responsive to electrical stimulation. And also, again, the liquid metal actually enhances the fracture toughness and the durability of these materials. So we can kind of poke at these, cut them or whatever, and the LCEs still remain intact. We can still pass electrical current through it. And there's some other interesting emergent properties that come into this that I don't have time to get into. Next step, so with this are to take architectures like this or architectures that Ryan has developed to create these soft actuators, soft artificial muscle that now use the embedded liquid metal, not just for the joule heating to activate these materials, but also for sensing, right? So in this case, this is actually an example of a kind of a self-regulating soft actuator that we can basically just track changes in resistance, then use that to determine when to send the next kind of pulse of electrical current to the actuator. And another kind of example here is again kind of following off of work that Ryan has done on 3D printing of these LCDs. See if we can kind of use these to kind of create more like filament-based architectures. We can overcome some of the challenges with basically the heating and cooling of these systems. So we can kind of do that in a much more rapid way. And then lastly on this topic, looking at integrating the LCEs with the thermoelectrics that I talked about, so we can actually get more digital control on that heating and cooling, and not just relying on just open loop joule heating and just passive, cooling in an ambient environment. So again, I'm kind of short on time here, so I kind of won't get too much in the details, but there's some interesting properties that also emerge when we start combining and mixing and matching these different kind of functionalities, right? So if you start adding the thermoelectrics and its energy harvesting capabilities with the LCE and its actuation, shape memory type properties, you can kind of create these materials now that can, sense an energy source and bend towards it to harvest even more energy. So things that kind of arise that again, sometimes you don't get with kind of more conventional material systems. This is actually just the last couple of slides here, so I'll just you'll have to indulge me and let me just show these videos. But this is the weirdest thing that we're doing, probably the most exotic in terms of what could be possible with some of these soft actuator technologies. This is actually getting away from a lot of the existing paradigms and using electrostatics or using kind of joule heating or whatever for kind of artificial muscle, and instead using electrochemical redox reactions to create a soft actuator. And so, I unfortunately won't have time to kind of get into the kind of the underlying electrochemistry here, but I'll just present this as a teaser. But basically, this is kind of an actuator that kind of pulses using very low voltage. And then we can actually get reasonable work densities out of this, and actually those work densities increase as smaller and smaller we get these liquid metal droplets. And so by applying voltage using electrochemistry to perform redox reactions on droplets of liquid metal, we can basically get them to kind of act like these little individual kind of muscle cells that are basically capable of kind of modulating the surface tension to create this kind of actuator type functionality. So that's something, may or may not ever be practical for a kind of robotics application, but still something that I think might be worth exploring. So that's kind of it. I mean, where I want to go with this is to work with you guys on seeing if we can harness some of these technologies for robot hands and dexterous manipulation, right? I mean, you all have all sorts of exciting test beds and approaches to kind of looking at say in hand dexterous manipulation, for example. Some of the work that we've been doing on kind of creating these sticker-like electronics that might be able to be used to augment the sensing capabilities of these kind of robots. That's certainly one. Using different types of soft materials, and also we've had like some recent work with Nancy Pollard on some more foam-like hands for also kind of creating soft robotics. So I'll kind of actually just close with some of that work that she's done. So any case, I really do again want to apologize for the late start, and also that means that we only have a few minutes here left for a Q&A. So thanks, and I'll take any questions.
Any questions?
Say just a little bit about the energetics and the physics underneath your redox actuators.
Yeah. Cool. Sure. So let me just I'll just go to this one. Actually, no, I think this slide might tell you a little bit more. So what we're seeing is basically we have liquid metal between these copper plates, and the liquid metal is in a reduced state. So we've removed this oxide skin that the liquid metal has. So in that reduced state, the surface tension of liquid metal is the highest of any known fluid. It's about 10 times higher surface tension than water, right? So about close to a joule per meter squared, which is pretty extraordinary. And then by applying a little bit of voltage, we grow an oxide skin, just a few nanometers, right? What that does is basically kills the surface tension. It goes from like a joule, like 0.7 joules per meter squared down to like virtually zero. And so now the liquid metal has no basically ability to hold load, right? And so if we have some type of load on our actuator, basically you'll just give way. And then the second we remove that voltage, or do a reverse kind of reducing voltage, then suddenly we go back to that a reduced state. And so that's what you're kind of seeing in real time in these videos.
Governs the rate at which you can grow that oxide layer.
It's just the time it takes to grow and then dissolve that oxide skin. But the oxide skin, like I said, is only like a nanometer thick.
Yeah.
So quite fast. Yeah.
So is it fouling over time? Basically, it will exhaust its ability to generate the substance.
No, so long as there's oxygen in the environment, it's not gonna do that. What happens when it does kind of foul is if we try to encapsulate everything in a gel, like an electrolytic gel, then sometimes we do see issues there. So still very much a work in progress. This is just kind of pretty recent results here.
Lots of bubbles rising.
Yeah, so that problem is actually, so to get in the reduced state, we have to kind of play around with the pH. We're using potassium hydroxide. The problem is we have an aqueous solution of potassium hydroxide. There's electrolysis going on. Even the voltages are low, they're still just high enough that hydrogen and oxygen bubbles are forming. So that's what you see there. Yeah.
And surface tension tends to go with not just area, but almost like well, I guess in this case it's area. So it just makes you have it parallelized would help further to have like Lots of little, almost bubbles. and
Yeah,
stuff.
it's definitely, yeah, if you go down to droplets, right, because it's like the perimeter, you know, the volume ratio or whatever, so, yeah, the smaller we go, then, you know, the larger those ratios are, so it definitely helps. So in principle, if you got these down to like a sub-millimeter scale, I mean, they're already actually quite small, but if you got them even smaller, then I think it could potentially be viable, for some actuator applications, yeah.
So, global warming is gonna cause a need for clothing that is cooling, and I'm curious whether any of your devices that you showed that generate electricity from heat also cool at the same time, or
They do.
are they separate?
They do, yeah, I mean, I don't have any videos, but, you know, I'll just show you a quick slide here of just the cooling performance that we get. So this is something that we actually haven't published yet, but and unfortunately, I don't have a scale bar, so you can see what these temperatures correspond to. So, but no, we can get down to, forget off the top of my head whether it's, you know, 5 degrees C or 10 degrees C, but quite very noticeable, the cooling that you get. The performance that we're getting with these soft thermoelectrics are equivalent to the rigid thermoelectric devices, but the fact that it's soft means that you can have very intimate contact with the skin, so you'll get much more of that cooling sensation.
I see the survival suit of the future.
That's right, yeah. Yeah. Post-apocalyptic future, right? All
Can I
right,
ask you a question while you're on the slide?
sure, yeah.
Mechanical sintering is kind of like easy to work with when you're talking about sensing in high deformation.
Right.
You have to actually mechanically sinter these in order to get them to conduct heat well.
No, so, we've gotten away from mechanical sintering. We have this new formulation here. So it's conductive as it is.
Using the silver.
Yeah, so in addition to the liquid metal droplets, we put silver in there too. Not so much silver that it degrades the stretchability, but just enough to bridge the gaps between the liquid metal, so we can get that percolating network. Yep.
Any other questions? With that, let's thank our speaker one last time.